lot of you guys showed up today on this Friday afternoon. I hope you're enjoying the pizza. It's my pleasure to introduce Peter Norvig.
My pleasure to be here.
The Director of Research at Google and the teacher of the Audacity course, which attracted more than 150,000 students online. And a very illustrious career at Berkeley before that, and of course at smaller companies. So thanks again for coming and reaching out to us.
Great.
It's really a pleasure to have you here. I guess so I thought the way we could do this is we'll just kind of, I'll ask you questions, and there's a bunch of questions up here on the forum, and then maybe we could open it up to questions
from
the class, either during as we're talking or at the end.
Yeah.
And are you still up for doing questions the whole time?
Yeah, I think that makes sense.
Okay, so we were saying the questions, you guys really come up with nice questions. Like I was intrigued by almost all of them. And so we thought we didn't want to cut that short, so we're going to do questions the whole time, and then we'll do a blog post with the coding part later.
Right.
All right. So we're here in an AI course. I guess my first question for you is like what do you think is important about AI, and what's the relevance of AI to society and the problems that are facing society today?
Okay. I guess I see, so first say, well, how is AI different from computer science? So computer science is figuring out how to solve problems and mostly focusing on problems that you know how to solve. And so then AI would be solving the problems that you don't know how to solve. Right? So making bank software is hard to get everything right, but you know what the answers are, that the deposits should equal the withdrawals and so on. But driving a car is hard in a different way, that there is no one answer of exactly what route you should do and where you should steer and how hard you should brake. There are constraints. You shouldn't hit the guy in front of you and so on, but there's no one perfect exact answer. So that's one reason why it's harder. The other reason why it's harder is that the inputs aren't as clear. Right? So in the bank, you get a deposit for $111.12. You don't get a deposit for, about $100. But in AI, everything you get is uncertain. So it's really dealing with uncertainty both in the problem specification and in the inputs that you get.
So a lot of people in AI talk about the sort of conflict between the traditional symbolic methods and the probabilistic approach to solving problems and dealing with uncertainty. What's your take on? And we talked in class. We read this Jane, Probability Logical Science, and talked about the connections between the two. What's your take on that conflict? I would say conflict in the field, in the research field.
Right. I think so. I've been in the field long enough to see this shift where AI, when I started, was focused on these logical methods and the search methods, stuff at the beginning of the book. And it has since shifted more to these probabilistic and machine learning methods, stuff at the end of the book. And I think it shows a maturation in the types of problems that you're willing to take on. Right? So if the problem you're trying to solve is playing chess well, then using logic is a good way to go, because everything in chess is well defined. You know exactly what the goal is, we know exactly what moves you're allowed to make. You can see the whole board and every piece and exactly where it is on the board. It's not like, oh, there's a pawn somewhere over there, I'm not sure what square he's on. We know exactly what square he's on, so logic works great. But once you start getting into the real world, logic breaks down. That's why we need probability.
So how does AI fit into Google?
I guess one answer is AI is everywhere that there's data, and there's lots of data at Google. So everyone has to understand how to deal with that. We offered an internal machine learning course, and we got 6,000 people signed up.
Wow.
And that's small by Andrew Ng's standards. He gets 100,000 or so on, but 6,000 people within one company all need to know machine learning. So I forget exactly how many engineers we have, but that's a significant portion. And so everybody has to know enough to say, I have some data, I want to be able to do something with it, make some inferences over it, and I need to at least speak the language to be able to call some routines and understand what comes back from it. So that's one level at which AI is everywhere within the company. And then there's other parts where there's just really hard problems. So we're trying to do computer vision, we're trying to do language understanding, we're trying to drive cars. Now we're trying to do stuff with robots, and that's more sort of traditional hardcore AI, but that's for a more limited number of people within the company.
So this is one of the questions that's farther down, but what are you guys doing with robots? There's all these big acquisitions that just happened. I'm sure everybody's asking you about
I don't know. Right, so that's a separate thing. We had a bunch of stuff we were doing within my group, and some of them are still doing it, and some of them left to go off with this group under Andy Rubin. So Andy was had a company that we bought that did the Android operating system. He's always loved robots throughout his whole life, and that's why he called the operating system Android. The joke is he should now call, now that he's working on robots, he should call it cell phone. But it's internal stuff so far, and you know, and I've heard some rumors, but I haven't even seen the big picture yet. So I'm scheduled to go meet with them, and then I'll know, but I probably won't be able to tell you.
So why is Google so secretive? I've asked actually other people at Google about that. I've asked that question. I've gotten that answer. I don't know. And I can't talk about it. If I did know, I couldn't talk about it.
I think one thing we've done is say that we're not going to announce products. We're not going to say, here's our roadmap. We're going to say, here's what we have. We think we should be judged on what's real, not what's imaginary. So I think that's part of it. Some things we're secretive about because we're in an adversarial relationship. So we have to defeat spam. If we said, here's what we're doing to defeat spam, then the spammers can have one step around us. So that part has to be confidential. Some stuff is for competitive advantage. So for example, we never say exactly how many computers we have. And the reason we do that is we don't want the guy at Microsoft to say, see, Google has these many, so you have to buy me the same number. We want them to have to guess at that.
So going back to what you were saying about a roadmap, I think something relevant to me as a new professor here, and maybe also to a lot of you guys who are students and sort of trying to map out what you should be working on and what direction you should go in your career. How do you decide what your roadmap is? And what's your advice to us as we think about what to work on and what problems to tackle? And how to use the technologies that we're learning in the course to make the roadmap?
Yeah. I guess you start at two ends and try to make them meet in the middle. So you find something that you're interested in where you can push the boundaries of knowledge, and you find a goal that you want to go to, some problem that needs to be solved, some need in society, and then you see if the two match up.
How do you know if they match up?
I guess you envision a solution. You say, can I get from where I am to someplace else? And that's always hard, right? Because the way
it's like
things
an AI
work.
search problem.
Yeah, right. Right. And you can do. Some people have different strategies. Some do depth first. Some do breadth first. Some do bidirectional. The engineers tend to do more the depth first, and the product managers more the bidirectional. Figure it out.
So that makes me think of another question that was up here. I don't know if I should be trying to find the question or just going from memory.
You can go from memory.
Yeah, so maybe at the end we'll go through and see if I miss any. But like one question was about the connection between AI and what I would call cognitive science. How do the algorithms that we're writing down relate to how humans do computation? Do you think that Bradford search says something about our brains?
Right. And that's a great question, and I think it's important to keep the two separate, but it's useful for them to stimulate each other. And I know this is another change in the field, is that we've gotten more serious and maybe more mathematical. So when I was in grad school, it was acceptable to write a paper that says, here's a new model of such and such, and we get this performance on this task, and it's a cognitively viable model, for the following hand-waving reasons. And then, you know, and if somebody says, oh, well, you know, you only got 82% and this other method got 85%, you could say, oh, yes, but we're more cognitively viable. and then if they said, but, you know, the brain does it this way and your thing does it this way, and we said, oh, yeah, but it's more efficient this way. Right? And so I think, you know, if you're simultaneously aiming for two peaks of performance and brain simulation, you aim for two peaks, you usually end up in the valley in between them. So you should really pick one or the other and say, am I doing cognitive science? Let's try to understand that. Or am I doing computer science? Let's try to get the best solution. And then your best solution can be informed by what you know about cognitive science, but you shouldn't pretend that you're doing cognitive science while you're trying to find it.
So here's another related question, actually, is the one that's up here, and this was the top voted question in the class. So when we do these problems with machine learning, where you learn something with a neural net, or we talk next in class about naive Bayes and logistic regressors, what you learn is, what's actually learned by the system is kind of opaque to the human designer. We can't extract principles from the solution directly.
Right.
So the question is, like, is this a symptom of our fallibility as humans or something else? Why is this happening, and how important is it that we have models that we can understand versus models that work as well as we can make them work? And I think this is especially relevant with the deep learning thing. So another company, I forget the name of the company, but the company that Google just bought.
DeepMind.
DeepMind, yes, that does deep learning. So you have even more parameters that are being fit in even more mysterious ways in exchange for really good performance.
Right. So that's a great question, and you know, we could spend the whole hour on that. So I guess a couple things. So one is, you know, you have to make this choice of what are you going to deploy, right? So it often happens, you know, somebody builds a prototype, they use some machine learning system, and it improves your score. Now, is that enough, right? Should we just say, let's throw out the code we have now and replace it with this system? And we have different responses to that in different places. So within search quality, usually the answer has been, we don't have machine learning code in sort of the center loop. That's all done by human. We have people that we think understand stuff better. And what we do is there's lots of input.
Can you say what the center loop is, or is that?
So it's, you know, you score things, right?
Okay. So like I typed a query, and the center loop is what goes through the whole internet and tells me what page.
So if you look in, you know, the basic information retrieval books, there's this vector space model, and how many words do you have? Compare the words in the query, the words in the document, you get a score.
Yes.
And now, you know, our score is more complicated because there's more inputs. And there's lots of machine learning that tunes each of the individual inputs. But then in the end, they're all combined in a piece of code that was written by hand and hand curated. Microsoft, we understand, is more willing to have machine learning in the inner loop. Why are we reluctant? So a couple of reasons. One, you know, maybe we have more pride and we think we understand things. I'm not so sure. So we think we understand things, but we might well be wrong. You know, maybe this dumb SVM actually understands better than we do. But that's one reason. Another reason is we think that we're more participating in a game than Microsoft is. So Microsoft is more observing the world. If they make a change, their actions don't have that much effect on the world. Whereas if we make a change, that does have a big effect. Right? So we have to not only say what's true about the world now, which our machine learning algorithms can understand, but if we made a change, how would the world respond and where would we be in the future? And we don't know a good way to do machine learning over that. So
you're talking about people trying to game the search engine results and raise their rankings.
Right, right. So we say, you know, if we made this change, then you know, we get a jump, but then they'd react in a certain way, and maybe we'd end up the world would be worse off. And we think we understand that better than the machine learning algorithm does, because the machine learning algorithm can't gather data about the future. If we could do that, we'd be in good shape. And then one more reason why we think it's easier for Microsoft to have more machine learning in the loop, is that they can train on us, and we don't have that advantage.
You can't train Microsoft?
Well, we could.
You don't want to train Microsoft?
Right.
Interesting. So you said a machine learning algorithm can't get data about the future, but I guess that's a question, like if you imagine, like there's models about economics and agents and multi-agent systems talking to each other, and I've seen these models in simple domains elicit this kind of behavior where people get in the system, so the model decides not to do it.
Yeah.
We had a speaker like that at Brown a couple weeks ago. Do you think that there's potential if we make better algorithms? And,
yeah. So I think that's true, and you know, you can always do more, and we could get to the point where we trust more, and to some extent we are doing that, right? So we are trusting more. And it's also true that we have much more machine learning on the ad side than on the search side. And I think that's, to some extent, a historical accident, that when we built the teams originally, you know, the search team felt like their main job was to really understand the algorithms, and so they felt like they had a handle on that, and then the machine learning is just an aid to them. Whereas the ads team felt like, well, our job is to build a real-time system that won't break, right? So for the, you know, when we first built the ad system, the search index was updated once a month. And so it was really this batch system, and now we're going to build the ad system where there were 100,000 auctions a second. It's this real-time transaction system, and so all the expertise went on that. And then they said, well, now let's show better ads. That's not our core, so we're, you know, anybody who can help, we're more willing to accept that help. And so there was more place for the machine learning experts to come in and say, hey, this looks better.
So I still remember I was doing my PhD thesis proposal defense, and somebody had done an internship at Google that summer, and they told me that they could write a program and run it on the whole internet, like every single page on the whole internet, and it would run on Google's cluster in 10 minutes. And that just blew my mind at the time. This was probably in like 2006. How long does it take now, can you say, like to run on the whole internet? And you know, what does that mean for what these algorithms can really do?
Right. Well, it depends on what you want to do.
Yeah.
Right. But yes, so you know, it was an explicit strategy to make that easy for anybody to do, and especially to sort of tie in research with engineering. Right. So in some other companies, you know, research is sort of separated from engineering because you don't want to get the researchers caught up in short-time work. You want them thinking in the future, so you sort of put a wall between them. And then, you know, the researchers run MATLAB on their laptop, and they say, well, I look like I've got a good prototype here, and they pass it off to the engineers, and then the engineers have to throw the whole thing out and implement from scratch. Whereas what we do is tell the researchers, here's a copy of the internet. Don't you want to run on that? Right? And that's much more interesting than running on your laptop. And so right from the start, the researchers are working you know, with the real data, at the real scale, with all the right APIs. Now, the researcher might write an algorithm that's 100 times too slow to actually deploy. So when we say we've got a working prototype, there's still work for the engineers to do to make it you know, crash-proof and efficient and all that. But at least they're starting from something that was using all the standard tools, and they just have to iterate rather than throw it out and start from scratch.
So what's your role as the director of research?
I guess it's making introductions is my main thing, right? To say, here's a researcher, and here's another part of the company that has a need, and you guys should talk. So that's mostly what I do. And, you know, sometimes I give advice, why don't you try going in this direction? And then hope that people meet up and good things happen.
How does Google assess how happy they are with their research program? Like are they really, is it about papers, or is it more about deployments and actually getting this stuff running and being in front of people?
So everything at Google is about inventing new products or improving existing ones, and that's true for researchers as well. So that's what you get evaluated on. If you also write papers, that's nice. If you have patents, that's nice. If you interview and hire a bunch of people, that's nice. So all these things are kind of add-ons, but the main thing is working on products.
So like really putting them in front of people.
Mm-hmm.
So do you think there's value in the more academic side? I think one of the other questions somebody asked was like you were in academia at Berkeley,
Yeah.
and then you chose to leave, and then now you're in industry, and so speaking to a room of students who are currently in academia, but most of you are shortly going to be making decisions about what to do afterwards. How did you make the decision to go to one unit, and how do you advise us to think about that question?
Right. So I made the decision because of the scale that I wanted to work on, and so I felt like it seemed clear that I guess we didn't have the word big data then, but it seemed to me that something like that was happening, and that for me to make progress, I needed to have a lot of computing power, a lot of data, and a team of a reasonable size. And as a new assistant professor, I said, well, maybe if I'm lucky with the grants, I can have 3 grad students, and and I've got 2 computers each or something like that. But I don't think it'd be hard for me to grow beyond that, and I just felt like that was too limiting. And in industry, you can put together a much larger team.
That's great. So where did you? So when you originally left Berkeley, where did you go, and like what was that larger team like?
So I taught at USC, I came back and taught at Berkeley, and then I went to Sun Labs.
Sorry. I see. So you went to Sun Labs. What were you doing at Sun Labs?
We were doing search, basically. We called it information retrieval then. And it was sort of as the internet was just getting started.
Yeah.
And so originally our job was to search over Sun's documentation and do a better job of finding the right stuff.
I see.
And then we started to say, at one point we said there's these 2 things. There's this World Wide Web, and then there's also this Waze, which was Brewster Kahl's protocol. I mean, we weren't even sure which one was going to be better, but we started looking at those.
So there's a question about this is up here, AI back in the day, like about 30, 40 years. What was it like as a graduate student, and how have things changed between now and then?
Well, first of all, it's a lot of fun being a graduate student, so I can recommend that.
How many of you guys are graduate students?
Okay, great. And then AI was in a totally different space then. So it was logic-based, and it was sort of knowledge-based, which meant that if you wanted the computer to learn something, it was because a graduate student wrote down a formula for it. And so I was doing story understanding. So you read text, you parse it, you extract some information from that, and you try to do some inference, answer SAT-style questions and so on. And I was working, a paragraph at a time. It would take me like a month to write down the logical inferences for everything you need to know about that paragraph. And we thought that was pretty good. You could do a whole paragraph in a month. We were really getting somewhere. But then, the probabilistic approaches, the machine learning approaches started to come in, and then we soon realized it was much better to do the whole internet at a time, rather than just do a paragraph, even if you can't do quite the level of inferencing with the whole internet that we could do with a paragraph.
So then you felt more drawn to the statistical.
Yeah.
So what? Let's go through maybe some other questions from the students. So what's the most interesting problem? Like going from now, from back then to now, what's left? What's the most interesting problem that AI hasn't solved yet?
I think the most interesting problem is still the same problem that I worked on in my thesis, which is can we understand text? Right? Because I think that's where most of the knowledge that we've generated as a species resides, but we're not able to do that. So if we could really understand what was going on, then our machines could be much smarter. We can read the biology text or the chemistry text or whatever and know everything that's in it. So that's reading text, it's understanding diagrams and so on. I think also we probably have to learn some video, because part of the problem why it's hard to read text is the authors of the text assume that you're a human being who has lived a life. And if you haven't done that, there's a lot of background information that's missing. And maybe if you're reading a math textbook, you don't need to know that much about life. You just have to know that A follows from B and so on. But the rest of the stuff you do have to know, right? So, and we're not going to be able to encode all that, right? So we can say that a cat is a mammal, but you really you have to know stuff about, well, how big are cats and how do they move and so on. And our best hope for getting that is not in books, because we don't write so much about that, but in videos.
So what do you think that's relevant? So I'm a roboticist, and I actually kind of work in some aspect of that problem. I work on making robots understand language, and the connection between language and the physical world. So what do you think is the relevance of robots in general and Google's robotics work in particular, the robotic car and stuff, to that?
Right, so I think living in the world is important. Right, so you learn a lot from doing that, and so maybe the problem then is integrating reading and the stored knowledge we have with the knowledge that you get from acting in the world.
So like having some kind of multimodal system that's physically grounded, but also can read text. Have you heard of Tom Mitchell's project? We had a distinguished lecturer from CMU or Brown here a couple of weeks ago. Tom Mitchell, who's working on NEL, this system that reads the internet, and every day it learns to read better, so it's building up over time this knowledge base of facts.
Right.
What do you think of work like that? Like is that sort of that's the right thing, and that's what we should be doing?
So I think that's definitely right. So he has this, he calls it the never-ending learning. I think that's great. Right. There's a similar project at University of Washington.
Pedro Domingos?
Yeah, and Orientazioni, although he's now at the Allen Institute, and Dan Weld. So why don't we do never-ending learning? And the answer is because we're too fast. Right? So he has to do that because it takes him so long to read the web, is that he has to read continuously. Whereas for us, we could say, okay, let's read the whole web with our current model of what we want to do. And it's like, all right, now we're done. Now we got to update the model to something smarter before we can read it again. And so that's the bottleneck in the loop, is us being smart about what we want to do next, not the reading part.
So what's the relationship between these learning algorithms and what we as designers put in a knowledge into learning algorithms? How important is it for us as humans to be involved in this and in making these algorithms better versus having that?
Right. So far we need the humans because we don't know what the right representations are. Right? So if you have a domain where a good representation is a point in a multi-dimensional space, then we got pretty good learning algorithm. But if you have a domain where the representation is something that's more structured, like it looks like language is, there's trees of sentences, and there's arbitrary graphs of relations, and we don't have that good machine learning algorithms. And we like to have intermediate level representations, and we don't know what they should do. Now, some of this deep learning stuff can invent some intermediate representations, but it still needs help.
So you don't think deep learning is going to be the panacea?
No, and it's, to me it doesn't really seem that much different than back in the day, right? So yeah, there have been some really cool refinements. So you read some of these papers, and you say, why didn't I think of that? That's an amazing, clever trick. But when it comes down to it, most of the stuff is not because of those tricks. It's just because the machines are so much faster, right? That in the past,
so more data, more computation.
Yeah, in the past you ran it, and you got the improvement curve went up to here, and you said, well, that's the best I can do. That stinks. But now you run it 100 times more, and now the curve gets up to there, and you say it's pretty good. It was really the same curve.
So thinking of AI as these maybe less complicated algorithms, but running for a long time, it kind of fits into this one of the other questions about the Chinese room and strong AI. So the Chinese room is this famous problem proposed by the philosopher John Searle, where he essentially defines an AI agent as a person in a room, and they're given a big lookup table of the correct responses to sentences in Chinese. And the person doesn't understand Chinese, but they get an input from outside the room of some characters, and then they look up in the book, and they figure out, and the book says what the response should be, and then they hand it back out in the room. And if you have a big enough book, you basically get an agent that, to the external observer, it would look like this system is understanding Chinese.
Mm-hmm.
And the question that he poses is this system intelligent? Can it be said to understand Chinese? When the person inside the room who's doing these lookups doesn't actually speak or understand the language.
So what do you say about that? Well, first, in terms of the Chinese room argument, you got to agree with it because it's sort of a tautology. So what Searle says is, obviously there's no understanding going on in the room because the person doesn't understand Chinese and the book doesn't understand Chinese. So if the components don't understand, then the whole system can't understand. And so basically his argument, and then he makes the analogy that the person in the book is like a computer and a program. So his argument seems to be, if I stipulate that a program has no understanding, then I conclude that a program plus a computer has no understanding. And I agree with that. And so how could you not agree with that? But then he sort of slipperily slips to saying, now let's drop the conditional part and just have the conclusion that a computer could never have understanding. But that's faulty, right? You can't go from if A then B and then conclude B unless you've established A. And he doesn't make any argument for A, he just assumes it. And I think that assumption is the same as what you could call the Chinese bigot problem, right? So what Searle is saying is, well, I think, I understand, I know that because I'm a person. But the computers, they don't because they're made out of the wrong stuff, right? And you can make the same argument to say, I, Searle, I understand because I'm a white male college professor. But these other group of people, which is some minority group that I don't like, how could they possibly understand? Because look at what's inside of them. All they have is a bunch of neurons, and none of the neurons understand. So if they're made out of parts that don't understand, obviously they couldn't understand. And that's really the same argument that he's making against a computer. He's saying the computer can't understand because it's made out of parts that don't understand. But the person is also made out of parts that don't understand. And yet we feel that people do understand. So
you think that if someday we're going to have programs that really are intelligent, whatever intelligence?
Yeah, well, I think we're going to have programs
with strong AI.
that we interact with and treat as people.
Will they have rights?
That's a good question. I don't know. And I should also say that that's not that high a barrier, right? So, we already have technology that crosses that, right? So people love their teddy bears and interact with them, even though the teddy bears don't really do that much. But we're very willing to project human qualities onto other things.
So another question related to that, is this whole idea of the singularity. That someday we're going to have programs that are so smart and so intelligent that they're going to do the research that right now, and they're going to do the model configuration, and they're going to do all the stuff that we do right now, and we'll just be redundant. And our technology will start advancing much, much more quickly.
Yeah.
And either, depending on who you talk to, it's either going to be really awesome or it's going to be really terrible.
Right. So I don't know. And I think the second part is great, the will we notice, because if you look at all these Kurzweil-style plots, right, these exponential curves, and if you plot them on regular graph paper, is there still graph paper? Then they're exponential. If you plot them on log, then they're a straight line, right? So if it's a straight line, maybe we won't notice, right? So it's exponential growth, but it's the same exponential growth all the time, so why would that be any different? I think another issue is, this idea of the singularity, I guess the name comes from Vernabingi, the science fiction author, but it really goes back to I.J. Good. This is a statistician, worked with Alan Turing, and around 1960 or so, he said, well, if we can make a super intelligent machine, then we don't need to invent anything else, because it can invent all the future inventions. But he said that in like 1960-something, before we had the idea of NP completeness, right? Before there was this idea that there might be problems that are so hard that we can't solve them no matter how clever you are. And I think that puts a barrier on what we can do.
That makes me think of another question about quantum computing. So one of the...
Well, let me just say a little bit more about this, right? So, you know, I think being super intelligent isn't the only thing in the world. I think we as humans, we name ourselves Homo sapiens. We think that thinking is the key thing that we do. But being more intelligent doesn't solve all the world's problems. There's lots of things wrong with the world. It isn't like, if only Putin and Obama were smarter, or if the Palestinians and Israelis were smarter, then they could solve all the problems. No, right? Being smarter isn't going to solve all the problems. So I think don't put all your faith on that. On the other hand, my co-author on the book, Stuart Russell, has this analogy. He says, suppose that today we got a message from space aliens. And it says, hi, we're in our spaceship, we're headed towards Earth, and we're going to arrive, some people predict in 20 years, some people predict 50 years, some 100 years, some think we'll never arrive, but we think we're on the way, and we're going to have amazing new technology, and we'll let you know, we'll call when we get there. So if we got that message, do you think that the people of Earth would just say, oh, well, that's kind of cool and interesting, something might happen, but now back to normal? I don't think so, right? I think there would be big conventions and everybody would get together and they'd say, how are we going to prepare for these aliens? Well, we got that message, right? So we got this message that these, maybe not singularity, but a big change in how we interact with machines is coming, probably in half a century, plus or minus, and maybe it might not ever come. So it seems like we should spend some time thinking about that.
So there was a question about this actually, the disadvantages of AI. So we've been talking about how AI can bring us a lot. What are the potential crises that this increased computation and power may cause?
Right. So one of the things people worry about is this breakaway intelligence, right? So part of the singularity is, one team comes up with this model and it becomes super intelligent and it knows everything and nobody else is close. I don't think that scenario is very likely, but we should spend some time worrying about that because it is important that our society holds together because everybody is in check. That no one country can act unilaterally because there are other countries watching out for them, and in other spheres there's the same kinds of checks. Now, if you lose those checks and there's one entity that has complete power over everybody else, bad things can happen. So I don't think that's likely, but we got to watch out for it.
So if I had to pick one place where something like that could happen, like one organization, it would be Google.
All right, so I better watch out.
What is Google doing?
Well, it's interesting with this DeepMind acquisition. They made us have an AI ethics board.
I read about that.
Yeah. So we'll see what happens with that. So I think that's an issue. Another thing people talk about, my friend Steve Omohundro has written, if you write AI systems as utility maximizers, then you better be very careful about your utility functions because they might optimize something that you didn't want. And that's also very true. Again, I think there's enough checks and balances that I'm not that worried about it. But getting the utility function wrong is a big deal. And that's happened before, right? So in the U.S., we made a constitution 200-something years ago, and we made some mistakes, like whether slaves are people or not, and that was a costly mistake. We had to pay 100,000 lives to fix that mistake. And if you get things wrong with AI systems, you may have similar kinds of problems. So that's another threat. I think another one is inevitably there'll be more income inequality.
You said more income inequality?
Yeah. And it's not particularly an AI problem. I think it's primarily a computer science problem in general, that if you have more communication and if you have digital goods with zero marginal cost, then you're going to have concentration of wealth. So it's sort of a theorem that that's going to happen, because now you can sell to anybody in the world without additional cost to sale, and your marginal costs are zero, so whoever's epsilon better than everybody else is going to take a huge share of the market. And that's going to happen across all markets, and so there's going to be concentration as well. And that'll be bad for society, and we'll have to recover from that. I don't think it's particularly AI's fault. I think it's, once we turned on the internet, it was inevitable.
You don't think that would, like, there would be like I guess what might mitigate that is that even if there's more inequality, the ocean
Yes.
is rising, right? Like,
Yes.
so even the people at the bottom.
So there's more wealth, and you know, people talk about the Star Trek future.
Yeah.
Right. So Star Trek, you never see anybody paying for anything. Right? Nobody's poor. There's so much stuff that you don't have to worry about it. You can do whatever you want. You say, I want to explore new worlds and seek out new civilizations. We'll just go do it. And so I think maybe we'll do something like that. There was this thing over the summer where Switzerland voted on having a minimum wage for everybody, right? So you just get paid money for existing, and they voted that down. But I think we may end up going to something like that, right? If there is enough rising tide and there's wealth everywhere, I think there's a lot of inefficiency now of people spending all their time looking for a job. And if you told them, well, you don't have to look for a job. Now, it's true that some would just goof off and do nothing and be unproductive, but other ones would say, oh, I'm going to write my blog, and I'm going to have a small following, and that's good to society. And other ones would say, oh, I'm going to start my startup idea, and 99% of them would fail, but maybe 1% of them would generate enough wealth that it paid for the whole program. So I think giving people more freedom is good. But then you got to figure out some way to make them not just give up and drop out and do nothing.
So maybe now's a good time to open it up to the class. So anybody would like to ask a question, or if we forgot any of the questions, it's up there. This is just the top few. There's a whole bunch of interesting ones in the tail. So just raise your hand and call in.
Well, I'd be interested in hearing the answer to the third question there, just if it's, sitting on the screen.
Right. What aren't we going to do?
Let's see. So we'll probably be doing less driving. All right. So I think cars can do a lot of that. What else won't we be doing? I don't know. It's hard to predict the future, right?
But lucrative.
Yeah, at Google, we say it's difficult to predict the future, but we can make a good living on predicting the present. Right, so there's things like the flu trends, where we can look at our search queries and say there's an outbreak of flu in Cleveland, and the Center for Disease Control will also know that with high precision, but it'll take them 2 weeks before all the doctor's reports and everything filter in, whereas we can get it today. We can not predict tomorrow, but we can predict today. So what else won't we be doing? I don't know about 10 years, but I think at some point in your lives, and probably in my life, there'll be a lot of home robots. So you won't be doing the housework and stuff. And I don't know if it's going to take exactly 10 years. One way to try to predict is to go back to the PC industry and say, what year do you think we're like in the PC industry? And I think we're like 1976. So in 1976, you could buy a computer kit and assemble it yourself and run little toy programs and not do anything useful whatsoever, but have a lot of fun playing around with it.
Yeah.
But then within 10 years, you could actually buy a computer that was useful. So I think that's where we're at today. Within 10 years, you can buy a Roomba now and watch it go around. It's not that much better than not having it. In 10 years, you'll have very useful stuff. And I think some of it will be completely autonomous. I think there'll be some trade-offs between autonomous and teleoperation. So just like today, we fly drones and they do some stuff on their own, but they also have an operator on the ground. You may have your laundry robot that wanders around your house and picks up clothes and takes them over, but it may also be checking into a call center and saying, I'm not sure if this is a sweater or a cat. Should I throw it in the machine or not? And the operator said, yeah, okay to go.
You mentioned that technology can sort of enhance inequality, and that intelligence doesn't necessarily solve all of these problems. Is there a way to use AI to apply it to these different kinds of problems, not just search problems or how to drive a car, but the domains outside what would traditionally be these problems, like international conflict or something like that?
Yeah, so you can certainly write programs that can come up with solutions to international conflicts, but then the conflicts are a power game, right? So you might have the right solution, but do you have the ability to impose that solution?
Yeah, I guess I don't necessarily mean power games, but more looking at income equality in the U.S. and exploring different kinds of solutions that you could pursue.
So I mean, it seems like there's good possibilities for having economic modeling or simulations. Now it's hard for us to change what we're doing for a number of reasons. One is that we have so much polarization in where we want to go that we can agree. And second is we don't know what's going to happen, right? So if we change these policies, what would happen next? And mostly that's discussion is driven by ideology rather than driven by any facts about what actually would happen. So if we had better ways of simulating and people trusted them, yeah, we've used this model so many times before, it works, it's better than the weather prediction, it's more reliable, and it says we should do this, then maybe people would start trusting that.
This is sort of with that one. What sort of surprised you the most? What sort of advance surprised you the most from the past 10 to 15 years in AI and computing in general?
I guess, let's see. I guess I was surprised that support vector machines have done so well. That it's one simple algorithm that we didn't have before that has really taken off and shown to be applicable in a really wide area. What else is surprising? A lot of the computer vision stuff has gotten better really quickly. The speech recognition has gotten better in maybe a completely unsurprising way, which is mostly, make some small tweaks and you get 1 or 2% better. It's the same pipeline, the same basic theories that we had 10 years ago. But 10 years ago, I didn't want to use the speech recognition system because there were too many errors, and now I do want to use it better.
So kind of related to this question, you said that within 10 years or within a bit more, you might have home personal robots, and you said that one of the biggest challenges was natural language processing. I was wondering what other challenges remain for AI before robots can cross that barrier into the home.
Yeah, so there's lots of things. Stephanie can answer that better. They're not good at grasping stuff yet. We're not quite sure how to build them. So how do you make them powerful enough to do the things they should be able to do, not so powerful enough that they're dangerous, dexterous enough that they can climb up stairs and live in an environment that wasn't built for them, but was built for us. Whole classes worth of stuff.
So I find your answer to the disadvantages point really interesting, because I guess in some ways it's not a surprise, right? Like this is automation kind of leads to this, and it's been predicted by people for centuries. But there's a group of people, I think, pretty vocal, that believe that at some point we'll reach a level of intelligence that we can sort of automate away all of our problems. And do you think that's like a pipe dream or a way to justify things, or do you think that's actually a realistic reason to approach AI?
Yeah. So I guess I don't believe in intelligence solving all problems, and I was skeptical about that, and I had a conversation with Kevin Kelly, and he had a word for it. He calls it intelligentism. Right. So it's this belief that intelligence is the one criteria that matters, and I think it's because that's what we're good at. That's what we stress. And if we were talking cheetahs, maybe we'd say, well, speed is the important thing. And if only we could build the ultra-fast machine, then we could solve all problems. If we were elephants, we would say, well, strength is the most important thing. We're only ultra-strong to solve all problems. But I look at exponential growth in other areas. So we've gotten really good at blowing things up. Right? So if you go from the bow and arrow to the hydrogen bomb, we've had great exponential growth. But then if you look at the effects on what happens in the world, the hydrogen bomb didn't really have that big effect. So maybe it stopped the war between the U.S. and Russia, which would have otherwise happened. But in terms of what power can I project on the world because I have one, it turns out today it's not that much. And so I think you'll find a similar thing. People will be frustrated. Well, I built this super intelligent machine, and it can solve all these problems so accurately, but it doesn't. The world doesn't fall down in the face of it.
You were a graduate of Brown. Were there any
Yeah.
courses you took that were pretty formative on your career?
So I was actually applied math major, and I took a bunch of computer classes. It just seemed to be easier to graduate with an applied math degree than a computer degree. Let's see, I was going through some old papers recently, and I came across my college transcript, which I hadn't seen in 30 years, and I noticed a very interesting thing, which is relevant to the discussion on MOOCs, which is I failed artificial intelligence. Well, you guys are Brown, so you know that you can't fail. I got an NC. And it turns out there were two classes in AI at the time. This was, I went to Gene Charniak's job interview in the spring of my senior year, so he wasn't here yet. I got to hear him talk, and I said, boy, it would have been great if he had been here when I was here, but he wasn't. So computer science, or maybe it was applied math, had a class in AI that Peter Wegner taught, and I took that, and that was all the search stuff out of Nilsson's book at the time, and that was a good class. And then there was another class in cognitive science, Dick Millward taught. I don't know if he's still here. So this cognitive science class that was called AI and something else. And I remember taking that class, and I remember some of the books we read. I remember getting a lot out of it, but I had no recollection that I got an NC. So at some point I must have decided that I dropped out, and I don't have any recollection of why I did. So I think this is relevant to the MOOC discussion. When people say that MOOCs are terrible because the dropout rate is high, well, I dropped out of a class, and I feel like I got what I wanted out of it. Maybe completing it isn't the most important thing in the world.
How close do you think these machines should be in a way that humans think? I mean, traditionally I would have thought that a robot would be bipedal and would have humanoid characteristics, but right now you see a robot which doesn't look anything like a human between, but and the same with machines. I mean, you mentioned that SVMs do not behave the way you would want them, like you would traditionally think of a problem, but then they do the thing as well as they're supposed to be.
Right. So I think you want to design systems with two goals in mind. Right? So you build a system that does its task the best way possible.
Yes.
Right. So don't give it 2 legs just because we have 2 legs.
Sure.
Give it the effectors that it needs to do the task. But then one of the tasks it has to do is communicate with people. And so you have to figure out how it's going to do that. And does that mean that it has to speak natural language, or and does it have to have, what sort of models of people does it have? So to that extent, you need to do cognitive science because you need to understand how people work so that you can interoperate with them. You know, it doesn't mean that you have to speak natural language. You can provide some other interface, but it has to be informed by what the people find easy to understand.
Maybe one or two more questions.
Yeah.
What's the advice do you have for the grad students who are working on the projects that are aligned to what Google is doing? For example, the project Tango that I saw recently. I believe that visual slam is like the toughest problem that people have been working on.
Yeah.
And suddenly, like we saw a video from Google saying that they are working on similar thing, which is visualized in a very good manner.
Yeah.
So should we get intimidated because the Google is being far ahead of what we are trying to do, or like?
I think you should keep doing what you're doing and do a good job at it. Right? Maybe you do it in a different way, or maybe you do it better. You shouldn't give up. You know, you could apply to get a Tango device, and that might be fun to play with it and see what it can do.
So do you think consciousness is computation?
So, you know, consciousness is a tough question, and I think we'll figure it out. And I think when we do, we'll say that was the wrong question.
Fair enough.
Right? So we have some idea of what consciousness is, and I think we'll come to say, oh no, it's nothing like that. It's a completely different thing, but I don't know what it is.
Well, on that note, thanks again for coming. I'll see you guys on Tuesday.